where this shear strength is required. In your classes, you have been doing it not for soil, but for, let us say, there are two surfaces. This you have been doing in your high school classes. There are two surfaces, and what is the shear strength which can be mobilized, or shear force or frictional force you called it that time. So basic mechanics remains the same. And then I discussed that in case of soils, the failure is always in shear, means it is the shear which is it is called as mode of failure, and failure will be along a plane. This may be exactly a planar surface, or sometimes it may be a curvilinear, but when you look at this surface, this will be a rough surface depending on the particle size. If the particles are coarse, then you will have a rough surface. If particles are fine, then it may be a smooth surface. And we need the mechanics always, despite the fact that soil will not be completely elastic. We will be using the theory of elasticity. And also, uh, soil is basically a discontinuum. It is a discrete medium. Discrete medium means it's not continuous like steel. Even steel at micro level, if you look at when you go to the atomic level, then everything is discrete. But practically, steel we can take continuum, concrete we can take continuum, where the material is filled with the space is filled with material. There is no space. But in case of soils, there are grain to grain contact. So it is a discrete medium, and many times we use it as a continuum also when the number of particles is very large. So we can, with some caution, use those continuum mechanics theories. Whatever you have studied, theory of elasticity, etc., that is continuum mechanics. In your solid mechanics also, you have discussed Mohr circle and analysis of stresses. So those things we are going to derive from the elasticity theory. So this is not very, it's an important issue. You as an IITian, you should be very much thorough about your basic fundamentals. Maybe it may not be asked in the exam. So these are the simple things which you must know. Coming to the syllabus or the exam point of view, you should know what is Mohr circle, how to draw the Mohr circle, how to get the stresses. We expect that you know all these things, and I told you yesterday that we will be having special case that in general we start with the principal planes, where minor principal stress and major principal stress will be acting, and then we'll have to do the analysis. And yesterday we have shown that on any plane which is at an angle theta, I can always get the normal stress and shear stress. Either I can do mathematically by resolving the forces, or you can remember this Mohr circle. And what we do is this every point on this circle represents a plane. Plane means a stress state on a plane. So for example, this point is representing the the x coordinate is sigma 1 and y coordinate is 0. So on x-axis we are plotting normal stress, on y-axis we are plotting shear stress. So here it is sigma 1. So this is the plane which is being represented here. And then we go anti-clockwise direction. Anti-clockwise direction, if you have a plane at an angle theta, here we will draw a line at an angle 2 theta as per this equation, because we showed it mathematically that the equation of the circle is satisfied by the coordinates of these means sigma and tau, and they satisfy. So every point is going to represent normal stress and shear stress at a particular plane. And what is that particular plane? Plane we will be talking in terms of angle. Here we are not talking where this plane is passing. We are talking only in terms of angles. So uh, Same thing is going to happen with this plane, same thing is going to happen with this plane and this plane and that plane. And also, yeah, I did not mention it yesterday, if you take the plane in this direction also, the same thing will be applied. So we have discussed only one plane, but there are two planes in fact. So this is you can take theta from here also. So same thing is going to happen for that those infinite number of planes. So failure is going to take place along one of these planes. So to get the stresses, you have to take angle 2 theta, and then the x coordinate and y coordinate of the Mohr circle is going to give you the sigma n value and tau value. This is what we have discussed yesterday. Then we have started the direct shear test apparatus. And shear stress versus shear horizontal displacement. And I think we have done up to here, where we take some 3, 4, 5, 6, whatever possible number of points, and then we fit a straight line. This uh, this envelope, yeah, we were here yesterday, so let me take it a little bit in detail. So these are the experimental points which we have obtained from the direct shear test. So direct shear test means you have got corresponding to every normal force, you are going to get some shear force at which the failure is going to occur. And then from there we get the normal stress and shear stress. So these points, they represent, if I join these points, they represent the relationship for the failure to occur, corresponding to various sigma n value. And if you use this general curve, which is experimentally obtained, we are going to call it failure envelope. Failure envelope. And uh, generally, what we do is, rather than using a curve, we use a straight line. And this straight line we are going to use in our computations. And that straight line is called as Mohr-Coulomb failure envelope. So here we have represented the failure condition by this straight line. And the shear strength now, at any point I can find out the shear strength. Shear strength will be given by this equation, tau f. So this is tau f. Tau f is equal to y is equal to mx plus c. This is the simple straight line equation. So the intercept is c here. So this is c, and this angle is phi. So c into this value, so y is equal to mx plus c, this value into tan of phi. So this is one component of the shear strength, and this is another component of the shear strength. So it has two components. Shear strength of the soil will be having two components. One will be coming from the friction. Let me take this one as first one, internal friction, because you are familiar with this. You have been doing these computations in terms of mu into r. So that mu is nothing but tan phi. So this is the frictional component. It is due to friction between the individual particles, and also it depends on the work done and dilation or roughness. So it depends whether it is a rough kind of the surface or it is a smooth surface. And if it is a rough surface, then you can imagine that when the sliding is going to occur, and if it is on a rough surface, then there will be some dilation, means movement will not be exactly parallel to this plane, but it may be in this direction, slightly upward direction. So there is going to be change in the overall volume of the soil mass. We use the term dilation. Dilation means increase in volume whenever there is some rough surface, and initially the two opposite surfaces are matching with each other, and when the sliding occurs, then the upper mass is going to dilate. So there will be some component. So if this is the displacement, then there will be some component in vertical direction, one component in horizontal direction. And when there is some component of the displacement in vertical direction, it has to do additional work against the normal force which is acting from top. So you are going to have much more higher resistance being offered by such soils. So internal friction. So because of friction, there is one component which is given by this intercept. And second one is cohesion due to cohesive force. Now, sometimes what can happen, there may be some cohesive forces. The particles may be sticky. It is you can assume that these two surfaces are glued together. So there is some cohesive force between the particles. So because of that, some resistance is being offered, and this cohesion will be constant. Means everywhere, if I take sigma n at this particular level, then when the soil fails, it is going to offer the cohesion, which remains constant, but the frictional component keeps on increasing. That will be equal to mu into R, because R is increasing. So frictional component will keep on increasing with normal load, and cohesion will remain constant. This is one term here. I'm using Mohr failure envelope. I told you failure envelope is generally non-linear, and it is called as Mohr failure envelope, or Mohr failure theory assumes that this is a non-linear kind of the curve. But as I told you, we will be using a straight line. So straight line approximation of the Mohr failure surface, and then it is called as Mohr-Coulomb failure surface. So Mohr-Coulomb failure envelope. So this is the straight line which we have assumed that it is this was the curvilinear behavior, and we have assumed this straight line. Similarly, we have assumed straight line here. So this straight line is called as Mohr-Coulomb failure envelope. And these are two parameters, C and phi. They are called as parameter. So C is the intercept. It is called as cohesion. And phi is the angle. It is called as angle of shearing resistance, or also it is called as angle of internal friction.
Excuse me,
So,
sir.
yeah.
Sir, what is work done due to dilation?
I think I should not have confused you that much, but when you have asked, let me give you an example. Suppose this is the idealized failure surface. Uh, so there are soil particles, and the failure is going to occur along this. If I go to, let us say, if I go to, yeah, this figure, you can see here the failure surface is not exactly planar. It depends. There are undulations. Are you able to see? Are you able to appreciate this? So it is not exactly planar. You got my point? So if I am doing a test here, consider a direct shear test where sigma n is acting in this direction, sigma x is acting in this direction, and then tau is acting in this direction. So what is going to happen when you, now I draw this figure here. So it is tau, and here it is sigma n. Now when it moves in this direction, because of these undulations, this body will not be moving exactly horizontal direction, but it will be moving in this direction. So somewhere, depending on these asperities, we call them asperities or angularities or roughnesses. So there will be some component of the displacement in this direction also. So if I resolve it, it has vertical component, it has horizontal component. So the body is moving against this normal stress. So in addition to the work which you are doing here, you can find out work is equal to how much? Force into displacement. In addition to that, you have to give some energy which will be spent in working against sigma n. So if normal force is n and this is the delta v, so n into delta v is the additional amount of energy which you will have to give to make it slide or to make it fail. Okay, so shear strength will be high in that case. But if it is a very planar surface, same, all other things remain same, but the surface is plain, there will be no dilational component, no additional work will be done against the dilation, and the uh, resistance offered will be low. We will come to this point maybe when I conclude this shear strength, when we discuss very compact, dense soils and loose soils. At that time, I'll come to this point once again. Can I proceed further?
Yes, sir.
Okay. So let me. So this is. I go to now this lecture. So the same thing here. Straight line approximation of the Mohr failure surface is called as Mohr Coulomb failure envelope, and it has the equation is y equal to mx plus a constant. So this constant is c here, and this tan phi, and another constant we have taken as phi. Uh, these are called as parameters, shear strength parameters, and c and phi. These are called as Mohr Coulomb shear strength parameters because we are representing the shear strength variation as a straight line. C is will be called as cohesion intercept, and it represents the shear strength of soil for zero normal stress. In fact, mathematically, if I put sigma n is equal to 0 here, this is sigma n. So when I put sigma n is equal to 0 in this equation, tau f will be equal to c. So mathematically, it is the shear strength which is offered by the soil when the sigma n is equal to 0. We also call it normal stress independent component. Means if I am calculating the shear strength at different normal stress levels, then this component remains same. So this component will be remaining same. And another component is tan phi, which comes from the another parameter. Phi is the angle of shearing resistance. This I defined in the last slide also. Sometimes it is also called as internal friction angle. So angle of shearing resistance or internal friction angle, they are same. And what does it represent? So it is the this angle. Physically, what does it represent? Mathematically, you can always give this equation, but physically also you should be able to understand it. Physically, it represents increase in frictional strength. Say, if I increase this phi is going to give you this component, this component. So if phi is equal to 0, this component will always be 0. Phi cannot be 90, it can be 30, 40, 50, and so on. So if phi is high, this frictional component will be high. And physically, I generally say that it is the what it represents is how much is the increase in frictional strength per unit increase in normal stress. So it is one way of remembering it. Means it is going to give you the idea, that phi value is going to give you the idea that how much will be the increase in shear strength, the frictional component, per unit increase in normal stress. You know the frictional component is equal to sigma n into tan of phi. So if I increase sigma n by 1 unit, how much is the increase in the frictional component? That is represented by phi. You should you can always explain it here looking at this equation. So it's the frictional component. The first component, cohesion, is stress independent. Second component is stress dependent. It is a stress dependent component, and it is defined, the stress component dependent component is defined through this angle phi, and phi is high, that there will be higher increase. Phi is low, there will be lower increase per unit increase in normal stress. So I think I'm clear. What I'm saying is if I increase 1 unit here, if I increase delta sigma as 1, how much is this? That is given, that indication is given by this. So this also I had explained that cohesion is due to cohesive forces, and internal friction is because of individual particles, and work done due to dilation or roughness. It is normal stress dependent component. Now, this is something which you should remember, though we will not be using it much. Failure theory, it is general failure theory which was suggested by Mohr. And what Mohr suggested was that in case of soils, in steels it is not going to happen, in concrete it is not going to happen. What happens in soil? Failure of soil occurs along a plane, that is important thing, and the mechanism is shearing. So that is a reasonable feature. We know that it is going to happen like this. Second thing, what he stated was there is a combination of tau and sigma n for causing the failure. So if you take this sigma n and this tau, it is not that every tau it is going to fail, or it is going to fail at maximum tau. No, uh, it there is a typical combination. There should be some relationship between sigma n and tau when the failure occurs. Failure does not occur for the plane having maximum tau. So don't think that if inside the body, so if I take a body here and it is subjected to some stresses, and if I want to know whether it is failing or not, then it is not that you find out the maximum shear stress. This is the maximum shear stress. This is the Mohr circle, and failure is going to occur. No, it's not like that. It is not like that. So here I had drawn this this uh, non-linear failure envelope, and the failure is going to occur at this point where the failure condition is met. So sigma n and tau f, you know, they are related with some relationship when we assume this relation as a linear relationship. So this relationship between tau f and sigma n for failure can be obtained experimentally. So what we are expected to do is we are expected to do tests, and then from there I can establish this relationship as we did in our previous case. So once this is established, then we can do the analysis. And another important assumption in Mohr theory is that intermediate principal stress, there will be some intermediate principal stress, and it has no effect on shear strength of soil. So it is only sigma 1 and sigma 3 that are going to play a role. Sigma 2 is not going to play a role. So this thing you should know. And we are going to use a simplified version of this, and we are going to use Mohr Coulomb failure criterion, means we are going to use a straight line. So let us now focus on this straight line. Not forget, we leave this curved portion. So what does this mean? So I have plotted this failure envelope here. On x-axis you have normal stress, on y-axis plotted us. What does this straight line really mean? Why I am calling it failure envelope? The reason is, I'll take some example. Let us say I take a point on this, point A, point B, point C, and point D. I have taken 4 points, and from origin towards x-axis the distance is same. So that means normal stress is same, and I am considering these points, they are representing some field situation. So in the field, somewhere the stresses are being represented by point A, somewhere it is the stresses are being represented by B, somewhere C, somewhere D. When I say stresses are being represented, means in the field, I am able to calculate sigma n and tau. I want to know whether it is going to fail or not. Say, for example, this is a stressed soil mass, and we have applied, or we take this case only, we have some stresses from this side, some stresses from this side, and I take a plane and I can calculate sigma n and tau. I want to know whether it is going to fail or not. So for point A, if I take this point A, x is equal to sigma n. So normal stress is sigma n and shear stress is equal to 0. So I have written it here. Shear stress is 0 and normal stress is sigma n. Now let me ask you people a question. What is the shear strength corresponding to point A? Shear strength means there are two things I am saying. One is shear stress. Shear stress is the actual stress which is acting in the field. And strength means how much it can offer to you against failure. So that is given by this straight line. I'm taking a straight line now. I could have taken a curve also. So here I have taken the curve. So here, for the sake of simplicity, I'm taking a straight line. So the strength is being represented by AC. You can calculate it from the equation y equal to mx plus c, or tau f is equal to c plus sigma and tan phi. So AC, this y coordinate is going to give you the shear strength. So shear strength is equal to tau f, and I'm writing it AC. Now you can compare whether is the shear strength is higher or the shear stress is higher. So for this case, it's very simple. Shear strength is much higher than the shear strength. So tau f is more than tau. It's not going to fail. So the body will be remain in equilibrium. If I take another point, another location where stresses are being given by point B. So again, normal stress is sigma n, and the shear stress is the y coordinate of point B, this much. So that is AB. So let me write it here at point B. Shear stress is A to B. Shear strength is same. Tau f is from A to C. And still tau f is more than tau. So still it is stable. Now I take another point C, which is exactly on the failure envelope. So for now, shear stress is being represented by AC, and shear strength is also represented by AC here because sigma n is same. So tau f is equal to, you have to write it here. Tau f is equal to tau, and this particular condition is called as limiting equilibrium, means it is just in equilibrium. If you increase tau maybe 0.00001, it is going to fail. It is going to be unstable. So this particular condition is called as limiting equilibrium, means maximum it can go up to this. Now what happens at point D? Now the shear stress is AD. So, and shear strength still is AC. Now tau f becomes less than tau. The shear stress is acting shear stress is A to D. So it is larger as compared to. So in fact, this point, uh, the soil might have failed. In fact, this stress state will not be existing because as the stress increases beyond C, it's going to fail. So here, theoretically, mathematically, I can calculate, okay, this point is going to fail. So what it gives me is, it's very easy that if I take this region, any stress state in the field which is lying here in this region, it is going to fail. It is not stable. So that is the thing which you people will should remember, and it's very important. Now, before going further explaining these things, I will in principle discuss one more test here. and that is triaxial strength of soil. We will be discussing these tests again in detail. Presently, I am discussing only the philosophy. So what is done here? This is a cell, and in this cell, this is the soil sample, and soil sample will be subjected to internal, there will be fluid, generally water. Water will be filled up here, and some pressure will be applied from all sides of the specimen. So sigma, I'm calling it sigma 3. So from all sides, the pressure is acting. And we will call it hydrostatic state. All sides, water, pressure acting on the specimen. So if I take any point inside this soil specimen, sigma 1, sigma 2, and sigma 3 all are same. If I represent this particular stress state on a Mohr circle, then you know the center of the Mohr circle has this coordinates, sigma 1 plus sigma 3 by 2 and 0, and radius is equal to this much. And if sigma 1 and sigma 3, they are same, so this will become sigma, let us say sigma 3, and radius is sigma 1 minus sigma 3 by 2. So the radius will become 0 for hydrostatic case. So Mohr circle will be a point. I'm representing it here. So here at this particular point, so at this particular point, the Mohr circle will be a point here because sigma 3 and sigma 1, they are same. Now what I do is I apply additional force from this side, additional stress from this side, and I'm calling it sigma D or delta D, and keep increasing this delta D. So what is going to happen? From the top, the stress will become sigma 3 plus sigma D, and from the sides, it will be sigma 3. So when you apply the deviatoric stress, I'm going to call this additional stress in the vertical direction. It is called as differential stress or deviatoric stress. Please remember both the terms. And this is applied additionally in addition to sigma 3. So let me plot it here once again. This is a case where sigma 3 is acting from all the sides. Sigma 3, sigma 3, sigma 3, sigma 3. And what I do, I apply additional stress. Additional stress I apply. So additional stress I apply. So the vertical stress becomes sigma 3 plus sigma D. Now what is going to happen? The radius of this Mohr circle is now going to increase because now sigma 1 has increased, sigma 3 remains the same. So once you apply some value of deviatoric stress, you can draw the Mohr circle. So Mohr circle will be like this. I hope everybody will be clear. Now, what I do is I keep on increasing this vertical differential stress. So when you apply further, then you will be getting this Mohr circle. When you apply further, then you will be getting this Mohr circle. Now let me ask you a question. Please concentrate on this circle. I could not draw it very good. So you can consider this circle. Now think carefully. Every point on this circle is representing stress on a particular plane. Stress state means sigma and tau. If I look at all these infinite points, is there any point which is satisfying the failure condition? So even if I go here, 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 nowhere I find the failure condition is satisfied. I discussed it in our previous slide. The failure condition is going to occur when there is a point on the failure envelope. When the failure envelope is touched by this Mohr circle, then and only then there will be failure. So if I look at all these points are representing planes. So there is no plane which is satisfying the failure condition. But if I keep on increasing this difference between sigma 3 and sigma 1, so if I keep increasing this deviatoric stress, I'm calling it deviatoric, means it is in addition to sigma 3 or differential. So gradually, slowly and slowly, you will reach to this circle. As soon as you reach to this circle, you will find that there is a point here which touches the failure envelope. So it touches means here limiting equilibrium condition has satisfied. So it is satisfying now the failure condition. It is satisfying this particular condition which we had derived experimentally, that tau is equal to C plus sigma tan phi. At the moment, don't concentrate on C dash phi dash. I'll come to that later on. So what is the failure condition? Failure is going to occur if you are gradually increasing the principal stress, the major principal stress. There will be a situation where one of these infinite planes is going to fail. Now, can I think I asked you about last point also in this slide, point D. So is it possible that I can increase sigma 1 further? So mathematically or theoretically, I can say, okay, I have increased it up to here, but practically I cannot increase, because as soon as you reach this circle, it is going to fail. So this bigger circle is not possible. It is not possible. It might have failed. That's why I was saying that the soil might have failed. So you will not be able to reach up to this circle. Point which I want to emphasize is using this sigma 3 and sigma 1 and using this condition of failure which is satisfied at a particular uh, plane, I can derive very important relationship which you should remember and which will be very helpful in in solving the problems. Okay, now here one more thing. I said you can increase the following conditions may be adopted to achieve the failure of the soil. So this is what I was doing, that I was increasing sigma 1. Now you can appreciate that it's not necessary that you only increase sigma 1, then the failure is going to occur. Even if you decrease sigma 3, the failure can be induced. So it is something like this, that there is a building and building is having, this is a building and building is having good support here, good support of the soil here. And suppose someone excavates this soil. So when it excavates this soil, means you are excavating, you are removing the support, and this building can fall depending on the situation. Mathematically or mechanistically, let us see whether we can do it. We can, if we decrease sigma 3. So again, if I start with this point, let me come to this figure which I had drawn here. This is hand drawn. So initially, when you started the experiment, sigma 3 and sigma 1 was equal. Now you reduce sigma 3. So once you reduce sigma 3, sigma 1 will be here and sigma 3 is reduced. So you will have one circle. You further reduce sigma 3, you will have another circle. Further reduce sigma 3, you will have third circle. And you can mathematically calculate that up to how much I have to reduce this sigma 3 so that failure is induced. So as soon as it touches here, you can, your mathematics is supposed to be very good. You can tell me the relationship, sir. I can, this value is given to you, phi is given to you, C is given to you, and this initial value is given to you. You can mathematically calculate what is going to be this value reduce sigma 3 at which failure is going to occur. Even you can have another combination. Suppose I decrease sigma 3 and increase sigma 1. It is something like this, that I am excavating the support near the foundation of the soil and I'm putting more load on the building also. So what is going to happen in that case? So you started with this, you decrease sigma 3 and increase sigma 1. So the radius of the circle is going to increase. Radius of the circle further increases, further increases. So you can have many combinations. Point is, you must remember that the radius of the circle is given by this expression. And if you are going to keep this sigma 1 minus sigma 3 constant, the failure is not going to occur unless it is touching the failure envelope. Let me take another example. Let us say this is the failure envelope, and this is one condition of the body somewhere. This is sigma 1 and this is sigma 3. If you increase sigma 3 and sigma 1 by same amount, you are going to get new circle here. You are going to get new circle here. It is never going to touch it. But if you decrease them by the same amount, so maybe, I do not know. You have to see whether there will be some situation where it touches. So point is, you have to see whether the circle is touching the failure envelope or not. If it is touching it, failure occurs. It cannot go in this zone. It can remain in this stable zone. So using these fundamentals, you can solve very important problem. And now I come to uh, the Mohr-Coulomb failure criterion once again. Before deriving one important expression, I'll just make one comment here that generally in the field, you can do analysis in terms of total stress. There are total stress analysis. It is called as total stress analysis or effective stress analysis. You people know what is effective stress. In fact, when effective stress concept might have been taught to you, the importance of effective stress concept is it gives you grain to grain contact force of the soil. How much is the grain to grain contact force? So that force in fact is the effective force which governs the actual contact force between the grains and the shear strength. If you find out if this is one grain, this is another grain, then the shear strength mu into R is going to depend on how much is the intergranular contact force. So here you have to use the effective stress. So effective stress is the stress which governs the shear strength, not the total stress. So generally, uh, the analysis is done in terms of effective stresses, means sigma 1 dash and sigma 3 dash. If water is present, if water is not present, then you can simply write sigma 1 and sigma 3. So you have to do the, wherever you have to calculate shear strength, in general, there will be some special cases, but in general, you will be using the effective stresses. So make it a habit that we write the expressions always C dash, sigma 1 dash, sigma 3 dash. But even if you are not writing it, it doesn't matter. But we should remember that effective stress concept has to be used in general. Okay, now I come back to the this equation once again. This equation of straight line, tau is equal to y equal to mx plus c. So tau f is equal to c plus sigma n into tan of phi. So we should make it a habit that we write c dash plus sigma n tan phi dash and sigma n dash also here. Okay, so this is the shear strength. Now, uh, can we derive a relationship? This particular relationship is in terms of where tau and sigma n are being used. There are many situations where we will be using the principal stresses. So sigma 1 and sigma 3 we are going to use. So the same expression, or the same, I should not say expression, same failure condition. Same failure condition we can represent in terms of sigma 1 and sigma 3. So either we can represent the Mohr-Coulomb criterion in terms of tau and sigma n, or in terms of sigma 1 and sigma 3. So there are two ways. There are two ways of expressing the failure condition. So let us derive this equation, which is very, very important, and we are going to use it at many places. So now we want to derive the equation for Mohr-Coulomb failure criterion in terms of sigma 1 and sigma 3. So I want to know what is the condition between sigma 1 and sigma 3 when failure occurs. So I consider this test again. Sigma 1 dash is acting in vertical direction and sigma 3 dash is acting in horizontal direction, and they are principal stresses. So there are no shear stresses along these planes. So I plot this Mohr circle. Sigma 1 is here, sigma 3 is here. I am making a habit that I am writing sigma 1 dash and sigma 3 dash. And at the time of failure, this circle is going to touch the failure envelope, that is a straight line. So this is the point where it touches. Now I can very easily derive the relationship between sigma 1 dash, sigma 3 dash, c dash, and phi dash. So this is c dash here, this is phi dash. So what I do is I simply use this geometry, this triangle, this triangle. So I am dropped a perpendicular here. This is tangential. It is touching it. So this angle is 90°. And what I do is this radius is sigma 1 minus sigma 3 by 2. So this radius, sigma 1 minus sigma 3 by 2 will be equal to, and this is 90 degrees. So if I take this distance into, and this angle is phi, this angle is phi. So this distance, this is the hypotenuse into 10, sorry, sine of phi will be equal to sigma 1 minus sigma 3 dash. So now I calculate this distance here to here. This is sigma 1 dash plus sigma 3 dash divided by 2. And this particular distance is this is a c. This angle is phi, so this becomes c cot phi. So c cot phi plus sigma 1 plus sigma 3 dash by 2 inside bracket multiplied by sine phi dash, it will be equal to sigma 1 minus sigma 3 dash by 2. Now what you have to do is, this is the relationship. Now you can rearrange it, put sigma 1 on left hand side and every other things on right hand side. Then you are going to get this equation, which you have to mug up. So remember this equation. So sigma 1 is equal to 2c cos phi upon 1 minus sine phi plus 1 plus sine phi upon 1 minus sine phi. So this is the very, very important equation. It is called as Mohr-Coulomb failure criterion. Same, earlier we were representing Mohr-Coulomb failure criterion in terms of shear strength and normal stress. Now we are representing it in terms of principal stresses, major and minor principal stresses. Please remember these equations give you the condition of failure, means the limiting equilibrium condition at which failure condition is satisfied. So sigma 1 and sigma 3 will be related with these expression. From your mathematics, you can also simplify this equation a little bit more. So it becomes 2c tan of 45 plus pi by 2. You know what is tan of 45 plus pi by 2 in terms of cos phi upon sine phi, and sigma 3 dash into 10 square 45 plus 5 by 2. So please remember this, and if you find something wrong somewhere, please let me know. So these are the two equation, or one equation in other, which is called as Mohr-Coulomb failure criterion. And also we will be interested to know what is the angle of failure plane. So that also is very easily available from this diagram. So 2 theta is here. See, the failure was not occurring here, failure was not occurring here, failure was not occurring here, failure is occurring at this particular point. So this is 2 theta, this angle is phi, this angle is 90, and so you know 2 theta will be equal to 90 plus phi, and theta will be equal to 45 plus phi by 2. So this also you have to remember. But you have to remember, please be cautious. What is your convention? From where I am taking theta? That you should always remember. So you can remember this figure. This is sigma 1. So this is 45 plus 5 by 2. So the condition of failure as per Mohr-Coulomb failure criterion may be represented in two ways. That's what I have written here. Either you can write it tau equal to C plus sigma 10 phi, or you can write it sigma 1 is equal to 2C cos phi upon 1 minus sin phi plus 1 minus sin phi upon 1 minus sin phi into sigma 3. And one more note I have put here. That is, see, for the sake of simplicity, we have taken only half of the circle. In fact, it is the entire circle, and you will have another failure ended up like this. So the failure planes, these are also this will also be the failure plane. The orientation may be in clockwise direction or anti-clockwise direction, both are possible. So these kinds of the failure planes are going to develop. So we have taken only in one direction. Please remember, it is going to occur in the opposite direction also. So this is the Mohr-Coulomb failure criterion. Let me stop here, and if you have any question, please let me know. Is there any question? You will have to remember these equations. You have to remember this mechanism that if I start with some value of sigma 3, some value of sigma 1, I can increase sigma 1, and this is the parameter. These are given to us. So when this circle touches it, or I can decrease sigma 3, or I can decrease sigma 3, increase sigma 1. So you have to see whether this condition is satisfied or not. Mathematically, this is the condition which has to be satisfied between sigma 1 and sigma 3 for failure to occur. And one important thing I told you, that make it a habit or keep it in your mind, that stress analysis, wherever shear strength is required, we will be doing in terms of effective stresses. Okay, so let us stop here if there is no question.
So,
Yes.
so finally, when we are doing the structure strength test,
Yes.
then the failure which we would see after the specimen is taken out
Yeah.
would be at an angle of theta, right? Which
At
we
a
have calculated as 45 plus 5 by 2.
Yes. Yes. That will be at 45 plus 5 by 2. And see, there may be some deviation because we are approximating this curvilinear equation by a straight line equation. So there may be some error because of this, but that is beyond your syllabus or beyond your scope. It is higher order studies. At the moment, you have to remember that the failure is governed by straight line only. And when you find out this angle after taking out a sample, then this should be equal to 45 plus 5 by 2. So in
Okay.
fact, you can get rough value of phi. I'm saying rough value because the limitations are there. So by measuring this angle also, you can get phi value. Okay,
Yes.
that's a good question. Any other question? If there is no other question, let me stop here. Okay, see you. Bye.